Last week, Adrian Wynter of Microsoft published a paper reporting on a large-scale empirical analysis of the ability of large language models, or LLMs, to learn. The title of his paper asks, "Is in-context learning learning?" In this episode, we will distill the substance of Wynter's findings and look at what they tell us about the capabilities of the present-day LLMs and their progress down the path towards the holy grail of artificial general intelligence, or AGI. Thank you for listening and subscribing. I'm Alex Chadyuk, and this is AGI. Listen every Monday morning on your favorite podcast platform. In the previous episode, we gave the elusive term of artificial general intelligence a more precise definition, highlighting the necessary transition from narrow intelligence, which is learning to perform tasks within one domain at a progressively higher level of accuracy, towards general intelligence that calls for a capability to transfer the acquired knowledge to new domains that were not part of the training. Note that when Wynter asks whether LLMs actually learn, the question is not as trivial as it sounds. Consider this. When we think of a human learning a new task, we almost universally assume that the human comes out of this learning experience a different person, the one who has changed the very substrate of their brain ever so slightly to encode this new capability. At least, this is how we scientifically conceptualize human learning enabled by brain plasticity. Now consider the LLM. When we prompt ChatGPT with a new task, we may provide an example of how this task is performed with a different known set of inputs together with the correct answer, something that practitioners call a shot. We may even give the LLM the precise algorithm of how this task should be performed. But even when we get a perfectly correct answer in response, the LLM does not come out of this experience a different thing. It still has the same enormous set of weights that constitute the language model. The model itself is deployed on the same hardware. Nothing has changed. Where is the learning? To answer this question, the LLM researchers came up with the term in-context learning, implying that although the weights of the LLM do not change, the LLM is still capable of understanding the examples and explanations provided as part of the prompt or a set of prompts and responses that together form what is called a context. The LLM then uses this context to come up with a correct answer. However, an LLM still looks like it has short-term memory loss. Once the context is gone, any learning, if it is indeed learning, is gone too. There's no doubt that the owners of the LLM can easily take your entire chat and include it as part of the next round of training of the model, but whatever can be gleaned from your interaction with the LLM will only be embodied in the next release of the model, perhaps in a few months or so. In real time, though, any learning outside of context of your own interaction with the LLM is apparently impossible, hence the term in-context learning. But back to Wynter's question, is this in-context learning really learning? To see how he answers this question, consider an example. A teacher asks a student a question in class. The student gives a wrong answer. The teacher gives an example of how a similar problem can be solved, but the student does not understand it. Then the teacher gives another example, after which the student gives the correct answer. Most people will agree that it is probably fair to say that the student has learned to solve this problem. Wynter's experimental design mimics this intuition. He picked a few problems of different complexity and, for each of them, created a large number of relevant examples that would usually help in solving the problem. He then fed these problems at a large scale to different LLMs and looked at the success rate in solving the problems as a function of the number of examples provided as part of the context. His finding, the more examples the LLM sees, the more successful it becomes in solving the problem, which leads Wynter to the conclusion that LLMs do seem to acquire knowledge when analyzing the examples provided as part of the context. Notice here the same methodological trick that Alan Turing used in answering the question of whether machines can think. He said, "I don't know the answer, but I hope we can all agree that if the machine can win the imitation game against a human, it will be pretty awesome." Wynter does the same thing by redefining learning from an abstract and often unseen process to an objectively measurable capability. We will be coming back to this distinction a lot in this season. Here, however, we will highlight another research question Wynter poses as part of the same paper. He asks, if an LLM is capable to learn to solve the problem from closely related examples, how well can it generalize to a slightly more unrelated problem? Let's come back to our classroom example. Imagine the teacher asks the student about the sum of the angles in a right triangle, and then gives a few examples of triangles and the correct sums of their angles. By observing the examples and listening to the explanation provided as part of the context, the student gives the correct answer to the problem. But now, the teacher asks about the sum of the angles in a square. This is what is called an out-of-distribution problem. If the training set provided to the student contained only triangles, perhaps distributed widely across different sizes, angles, and colors, but there were no squares, we would say the squares were not part of the training distribution. So trying to solve the problem for a square for the first time is what we call an out-of-distribution problem. Thus, the second question Wynter asks in his research is, in other words, how well LLMs can solve out-of-distribution problems. The answer is much less encouraging. While LLMs showed good results in learning to solve within distribution problems, they were mostly unable to generalize well out of distribution. A less generous observer would say that such in-context learning is more akin to learning by rote. We pay so much attention to the ability of intelligent agents to generalize their acquired knowledge both in past and future episodes of this podcast because it is such a crucial part of what we call artificial general intelligence. One may even say that it is the make or break condition for someone evaluating an intelligent agent to say that this is AGI.